Hello, and welcome to section 4.4. We're going to learn a couple new shortcuts today, and we're going to talk about one shortcut that doesn't actually work. Here are the solutions for 4.3. And you guys had a couple proofs. Okay, we're going to be working with side, angle, side, and one interesting one called HL. So yesterday we did side, side, side. We're going to work with side, angle, side today, and then we're going to work with HL. And I can show you guys kind of this in class. It makes a little more sense. So basically, we have what's called this included angle. So we're going to fix to the side lengths, and we're going to have an include angle. If I have two fixed side lengths, the angle that is between those two fixed side lengths are the same, then the two triangles have to be the same. So, and in class, I'm going to use, so we're going to fix this side length and this side length, and then we're going to fix that included angle. So as long as these three objects are the same, this value right here has to be the same, and it can only create one triangle. And again, this will make more sense when I show this in class. It's kind of difficult to teach over a video, so I'll do another demonstration in class for you guys. So this is side, angle, side. This has to be the included angle. So that word right there is important. All right, so here's a proof. We're going to use side, angle, side for this. We're going to show that two triangles are congruent. So we're given that the lines are parallel, BC and AD are parallel and congruent. So let's see if we can go about this. So we're going to show three parts are congruent. I already have two of them congruent. Or sorry, one of those. One of those is really obvious though. All right, so let's start with BC. It's congruent to DA. That is given. And then BC is parallel to AD, also given. Now, as a result of these being parallel, hopefully you guys start to recognize this Z shape here that I've been kind of telling you guys about. These angles here and here, I'm going to call that angle 1 and angle 2. Those angles are going to be congruent because they're alternate interior angles and the lines are parallel. So angle 1 is congruent to angle 2, alternate interior angles. And then my last side is going to be CA and AC. And that is our reflexive side. Both triangles share that segment. Now, one thing I'm trying to get you guys in the habit of doing is marking down, we have a side, we have an angle, and we have a side. So now I can use side, angle, side. So triangle ABC is congruent to triangle. Let's try that again. CDA. And there's a proof for you guys. So in this proof, I use reflexive and alternate interior angles. In the diagram, QS and RP pass through the center of M of the circle. What can you conclude about the two triangles? So this is kind of a cool problem. We have these two sides are the same because they're radii, and all radii are always the same. And so those two are also the same there. And then hopefully you see that these are vertical angles right there. So the two triangles are congruent by side, angle, side. All right, how about side, side, angle? Can you create more than one triangle with a given angle and then two sides? So now here, notice how this is the non-included angle. And this is very difficult to show. I can show this as well in class. But the answer is yes. You can take this side length here, and instead of being there, this side length could go there, and you could extend that. So you could actually create two separate triangles with two sides that are congruent and a non-included angle that's congruent. So these two triangles are not congruent, although they have three parts the same. So side-side angle doesn't work. This is really important. All right, and then we have this is the special one I was talking about, HL. HL works for right triangles only, so you have to have a right angle in order for HL to work. And this is the only case where you have side angle working. It only works for right triangles. And the proof is actually kind of neat. I can show you guys in class. It involves the Pythagorean theorem. So in a right triangle, we have two legs and the hypotenuse, and so HL says that if you have one of the legs congruent to one of the legs and the hypotenuse congruent to the hypotenuse, then the two triangles will be congruent. So this is a unique one, a special one that only works for right triangles. All right, write a proof. WY is congruent to XZ. I'm going to separate my triangles right away here. Anytime you have overlapping triangles, this is the strategy that I tell students is to, that didn't work out very well. Let's try again. Is to separate them. All right, let's separate them one at a time here. There's one of them, and there's the other. Okay. That will help you with your proof here. Okay, so WY is right there, and that's congruent to XZ. That one's right there. It says that WZ is perpendicular to ZY. That's going to create a right angle there. And then XY is perpendicular to ZY. That's going to create a right angle there. Okay, so we have a lot of information here. Now this is kind of unique because this ZY right here, that's going to be our reflexive side. This is ZY. This is Z and Y here. So this one's actually the same there. So really, I have a right triangle, so that's going to indicate that's going to be HL. It's not always going to be HL, but a lot of times if it's a right triangle, it will be HL. And then I have one of the legs congruent. So the legs and the hypotenuse is congruent, so we're good to go. All right, so what I'm going to do is start with WY is congruent to XZ. And that will be my hypotenuse. That's my H. And that's given. And then I have some perpendicular segments. WZ is perpendicular to ZY, and XY is perpendicular to ZY. Given. And what that does is that makes angle, I'm going to call this angle 1 and angle 2. So I'm going to say that angle 1 is angle 1 and angle 2 are right. Definition of perpendicular lines. Now I'm establishing that this is a right triangle. And then ZY is congruent to YZ, reflexive, and then the two triangles are congruent by HL. There you go. So that's an example of using HL in a proof. And here's the assignment for you guys. Again, there's going to be some proofs in there. Make sure you give them a try. Let me know if you guys have any questions, and I'll see you guys for 4.5.